malware analysis possibly. So this is slightly off the track. So I work in network security. So malware analysis is something which I don't do very often. So I thought I'll talk about the how the security has evolved over a period of time in the communication networks, and primarily the objective is to take you through the TOR traffic analysis. If any of you have heard this name TOR before, so it's a browser which is designed for providing the anonymity. So that is the objective. We have done some experiments using the TOR. So I'll walk you through those results as well. So let's begin with the basic question. So how security is actually provided in the communication networks. So before we actually see some of the security solutions, but maybe back then in the ARPANET's time, when the computer networks are first designed, so security was not the primary goal of the networks. So it was meant for some set of users who are trusting each other, and none of them are doing anything nefarious in the network. And primarily with two use cases in mind. One is the sending the emails over the network, and second one is sharing the files. Only with these two applications in mind, networks were designed. So rest of all things, whatever the internet that we see, is all the consequence of the evolution that took place in the network. So in that sense, whatever security mechanisms that we have and we use today are all the things that we retrofitted into the original network design. So the very first the security solution that was designed was the TLS connection mechanism, and for that matter, anything that security when we say, so these techniques primarily are meant to provide, of course, the secure connection, then the privacy of the end users, and sometimes we want to be anonymous in the communication. So meaning that neither the end parties would know who is accessing the data, who is consuming the data, and the client would really know who is the provider of the data. That we call it as the anonymity. So it is not always true that all the three of them are always available, but at least a subset of them, either it is secure, it is providing some sense of privacy. So if it is either way, then it is anonymous. So these are the three or four primary techniques that I will cover in this presentation. So one is the TLS, as I said. Second one is the virtual private networks, and then something called as the pre-net, and then finally we'll enter into the TOR, or it is also called as the onion router. So the best pronunciation for this is this one. It is the only T is written in capital, but the sometimes because of the enumeration, people also use it, but the official nomenclature says that you should not use that. So TLS possibly many of us would be familiar. So just the historical context, as I said, data was historically transmitted in an unencrypted network. Wherever the encryption, in fact, the before the TLS came, there were some security mechanisms people were talking about, primarily when you enter the password, and maybe when you use the credit card or banking application somewhere there, the payment channels were using the encryption mechanisms, but otherwise the rest of the internet was primarily uh, it was open. So meaning that without any encryption was operating. And the first time the security standard in the internet came in the year 1996. By that time, World Wide Web was operational, and there was few applications which were running. So people thought that it's actually going to take off. So that's when the security was introduced. And roughly 20 years later, in the year 2014, this consortium called as the Internet Architecture Board, in short, it is called as IAB, advocated security as the norm for the encryption, in the sense that by default you need to have the communication over the internet which is secure. So that's where you see many of the websites are now using the HTTPS connections. So it is not HTTP connections anymore. There are few sites still lagging behind, but nevertheless, majority of the internet websites have switched to the secured version. So now anything that you design and connect to the internet should be secure by default. At least it should use an encryption algorithm. So with that background, let's see how the TLS works. So this is not an exhaustive coverage on the TLS, but just to give the context, I introduced how the evolution took place, where we stand there. So in order to give that context, I have given this. So what TLS does is anything you want to secure, so you need to use a cryptographic algorithm. And what it does is it provides the end-to-end security to the data sent over the exchange over the network. So when I say the data exchange, it is basically two applications. We use the client server communication model. So one end is the client, typically that might be my browser, my email application, or anything else, a remote login application. So you can think of anything. So whether it is the WhatsApp, in all of these are voice over IP communication, all of these are applications. So these run at the client side, and there is a companion server which is going to facilitate this data exchange. So between these two, client and server, there is a tunnel that gets established, and through that tunnel, the data gets actually transmitted. So when I say the tunnel, this is the application layer tunnel. So it just TLS operates just above the transport layer, but slightly below the application layer. You can think of this as the layer between the, if you recollect the TCP/IP layer model, file layer model, so in between the application and the transport layer, this actually operates. And in fact, the name TLS came a bit later, but earlier there was one more protocol, security protocol called as SSL. So SSL, we had version 1, 2, 3, and then based on SSL 3, TLS was derived. So basically with better cryptographic algorithms and key exchange algorithms and all were introduced. And a key feature of this TLS is this is application independent, in the sense that you can use for any applications. So HTTPS or HTTP is one of the primary applications which is used on the internet. But other than that, you can use it to secure the emails. You can use it to secure the DNS. You can use to secure any application that you can think of, voice or IP communication, anything like that. So this, in that sense, this is application agnostic. So, and one key thing to remember is TLS does not provide the security to the data that resides in the computers, in the sense that till the data is handled by the application, it is not the job of the TLS. Once the application handovers the data to the TLS or the transport layer, then the security is provided by this TLS communication. So it's like at one end, till you cross that the application layer, so you need to have a different security mechanism if you care about the data security when the data is at rest. So when data is rest means it is residing, it is not moving. But when it gets transmitted over the network, the TLS will take care of that. So what it does is, by providing the security for the data in transmission, it ensures only one thing, which is the protection against the eavesdropping, in the sense that somebody sitting in the middle will not be able to read and make out what data being transmitted over the network. And it also provides security against the alteration. So modification and the eavesdropping, modification is a little hard to do, but eavesdropping is the easiest thing to do. So it provides the security against these two things. So how exactly TLS works? So in summary, if you, without going into the technical details of how the TLS works, so there are multiple versions of the TLS. 0.1, 1.1, so something like that. So initially the client and server agree on some version of the, what version of the protocol to use. It's mainly the minimum of what the client supports and what the server can support. Those two will be the version number. So let's say my client, my browser supports version 1 and the server supports 1 and 2 and 3, and the client will, let's say, I can understand only version number 1, then they fall back to version number 1. So although server can provide version 3 support for version 3, but it chooses to use version 1. And then once you choose version number, then you select the cryptographic algorithms. There are a range of cryptographic algorithms, encryption algorithms that you can use with the TLS. So the client and server negotiate and choose a set of cryptographic algorithms, and then the two end entities authenticate each other by exchanging the validating digital certificates. Normally, the client doesn't have the certificate. So in the context, the way we use the applications, it's only the server which has got the certificate, but having said that, it is also possible to have the client also to have the certificate. So the server sends the certificate, and then they mutually derive a secret key. So initially, the certificate is actually a public key. That is an asymmetric encryption technique. This asymmetric encryption technique mechanism is used to generate a shared secret key, and that secret key is actually used for symmetric encryption. And the data is actually secured, encrypted. Everything that goes over the HTTPS is all encrypted using this symmetric key encryption. So the asymmetric encryption technique is actually playing a role of only facilitating the derivation of the said secret key. And as I was referring, so if you look at the 5-layer TCP/IP architecture, this is where the TLS actually stands on top of the IP and the TCP. So from here to here, whatever you see is the TLS nation. So on top of that, you have the HTTP and the any applications that we have. So in some sense, you can think of that as the integration of this TLS into the application, but it is not actually the case. It exposes a set of APIs, and then you call those APIs and use the security mechanism to provide data security to the transmission. And there are, as I said, initially the handshake mechanism is done through this SSL handshake protocol, and then the cyber suit is actually selected, meaning which cryptographic algorithms you need to use, and that negotiation is done in the next phase. So once the data transmission actually happens, it actually indicates that whatever is chosen using this something called as the SSL alert protocol. So don't get confused by the name SSL and TLS. TLS is an upgraded version of the SSL. So still the names of the earlier versions of the names SSLs have been preserved here as well. So the more or less do the same thing. And the actual communication, the sequence of operations look like this. The browser says hello to the server, and the server also replies back So in that client hello, it to identify the TLS SSL version, what are these supported cyber shoots, and the server also responds back with an hello. Then the server presents its digital certificate. Here is my certificate, and then the client validate, because there is a certifying agency which has validated that, certified that public key. So using that, the client can actually, okay, this is authentic public key of the server. Then it generates one secret key and encrypts using that the public key which is shared by the server, and send it to the server, and server decrypts that and send it back to the client. That's how the authenticity of the client and server is actually established. Once this is done, then they derive the session key, and using that session key, the subsequent application data is encrypted, and then it is exchanged over the two. So remember, so now after this, both client and server are using only one key, which is session key, and this session key is periodically updated, in the sense that once its key is derived, it is not. For example, if you are in a so video conference, just like the meeting that we are having, not one secret key that is derived is used till the communication is ended, but it is periodically updated, in the sense that maybe, let's say, think that every 10 minutes a new secret key is derived, and then subsequently the client and servers use that newly derived key to encrypt the traffic and share the content. So that's how the TLS works. So this is the first the major security mechanism that was brought into the internet. And then came something called as the VPN. So the use cases for the TLS and the VPN were very different, in the sense that TLS was meant to provide the security and privacy to the a particular client joining the network and accessing the services from some public server. But the VPN was brought from a different perspective, which is so after the World Wide Web became popular, there were a lot of applications and the users. So they were having the offices at the different places in the for example, one office in India, second one in US, and within India it might have some regional and headquarter office in different places. So how do we connect to these offices seamlessly from one place to another place? So, for example, if I have a service, let's say I have some one server placed in the head office location, and if there is a regional office, let's say this is in Bangalore, and I am sitting in Indore, this is a regional office, and I want to access the services which is located at the headquarter in Bangalore, as if I am part of that network. So in order to facilitate this, the VPN concept was brought, and then so I don't want again the eavesdropper to make out what data being accessed, or what services I'm accessing. So there the VPN concept came, and again this was actually a big hit when it was brought somewhere in the again mid 90s and late 90s. This was actually very popular. So the VPN provides is this: if you have, I need to have a tunnel. Now the previous case tunnel was between one client to the one server. So as many clients as I have, those many times of different tunnels I have. But now what the VPN does is slightly it takes an aggregated view of the security and the privacy. The entire one office is actually can be thought of as having a single tunnel to the other office in the network. So that is the view. So if you have 10 different offices and 10 different places where your employees are sitting, so it is good enough to have 10 different tunnels to the headquarter. But within the one office, you might have hundreds of thousands of the employees, and all of them can make use of one security tunnel that is available. So many players like Cisco and others ones, they built appliances which provide such kind of the VPN connectivity, and this was realized through something called as the IPsec. IPsec was the primary sorry IPsec was the primary the technology that was available in the background, which facilitated provided this VPN connectivity. So what is this IPsec? IPsec is actually the previous one. TLS was operating above the transport layer, but this VPN brought that one layer below the connectivity. It is operating at the network layer. So in the within the TCP/IP communication layered architecture. So you have the IPsec or the VPN operating at the network layer. So this VPN and IPsec, there are two modes in which you can operate. One is called as the tunnel mode. Second one is called as the transport mode. So in the tunnel mode, the entire IP packet as it is transmitted. So when I say the IP packet, it is also the TCP or the UTP header, and it includes the application layer header. So everything from here to here, including the data and TCP header and the IP header, for all of this is you provide the security. So what you do is you take that original IP packet and then add a new header. In fact, two of them. One is the new IP header, and then the something called as the ESP header. And then there is a trailer just to make it align with the number of the bytes that you required, because you need to also indicate the length of the total field. So in order to facilitate that, so this trailer was introduced. And then there is an authentication trailer. So this is a cryptographic checksum that is calculated and put at the end of the so these arrows indicate on which part of the portion of the content the encryption is done. So IP header is encrypted, TCP or UDP header is encrypted, the data is encrypted. In fact, the trailer that you added will also be encrypted. This is just the some text to align it to the multiple of 32 bits. And then the new ESP header that is added up to the ESP trailer, everything is taken, then it is signed, and the cryptographic checksum appears at the end of this. So this is called as the tunnel mode. Excuse me, actually, I'm not feeling well. I'll just have water and come back. Give me 30 seconds time. Yeah, sorry about that. So this is how the tunnel mode of the VPN works. So let's move on. So that was the tunnel mode, previous one with the ESP header. So there is also one more kind of the operation that you can do, which is the with only authentication header added. So here the the content, whatever original IP packet is there, as if the IP header and the TCP header data is encrypted, and the entire the new IP header that you added, and then the authentication header is inserted between the original IP header and the new IP header, and this is yeah. So the new packet looks like having these many components, and then there is a send. It provides the authentication and the security. Here in this case, there is no trailer, and also there is no signature that is put at the end. Sorry. Similarly, we have a VPN operating in the transport mode, where the again you can have this transport mode in the ESP or with the authentication header. So if you use transport mode with the ESP header, so all that you do is the original IP header which was here is shifted out of the box, and then in between the original IP header and the TCP header, there is a new ESP header inserted, and then data as usual, the trailer to make it align with the number of the bytes that are required, and then the authentication trailer. So again, the what portion is encrypted and what portion is signed, that is shown by these arrows. So you use the transport mode with the authentication header. Only thing that happens but that is you insert an authentication header in between and then sign it, but the IP header is actually moving out of the box, and then it is coming and setting. So remember, this is not a new IP header that is added. It is the original IP header. It is just shifted out of the ahead of the authentication header. That's all it is changing. So from the TLS to the VPN, you have two different security mechanisms. So then people started asking, these were good enough. Even now we use the both VPN and also the TLS security as we speak. The majority of the applications in the web are using the TLS connectivity. But one thing was actually not going well, which is the privacy of the end users. So if, let's say hypothetically somebody is sitting in the middle of the network, and I and the person X keep talking once in a while, and let's say every day morning we keep talking, exchanging the data, maybe we say hello to each other and something like that. So that might give, even though the person in the middle may not read the content, but the timing information of who is talking to whom. So person X is talking to person Y, and at what time person X usually talks to Y, how long the person X talks to Y. So this information can be still found out if you are in the middle of the network. So now, in that sense, neither X is actually not traceable, and neither Y is traceable. Both of them can be identified. So how do we? People started asking, how do we provide better anonymity in the network? So can we talk or exchange the data without letting the other user know who I am? And the other user services, they are provided the data without knowing who the client is. So a first effort towards this direction was done through something called as the pre-net. This was somewhere around the year 2000. The first paper was published, I think, in the year 2000, where they advocated something called a peer-to-peer network, where it is a kind of overlay network on top of the TCP/IP network that we have. So you can think of some subset of the nodes are part of this network as an overlay network. They propose this pre-net. What it does, So as peer-to-peer network is not a client-server architecture in the sense that the browser and the server application that I gave is a model communication model which is based on the client-server architecture where multiple clients go to one server and get the content. But this peer-to-peer architecture is somewhat different. A set of the nodes are geographically distributed, and then they know with whom all they are connected, and then they ask the questions, do you have this data, can you provide this data, and then the data is distributed among these nodes. So if any of you use the torrent, BitTorrent, then that is an example of the peer-to-peer network. So here in this architecture, this was a kind of the BitTorrent network, but it is not the BitTorrent network. So the philosophy is still the same. What it did is it decentralized the content distribution in the network. Decentralized means there is not one particular server which is providing the content. So right now, if you access the content from the youtube.com, it is the youtube.com server which is giving you the content. So what this pre-net advocated is, let's not have one server, but let everybody become the data providers. So in that way, it is purely distributed data delivery model. And one of the primary the features of this pre-net is the anonymity, in the sense that nobody knows who is requesting the data and who is providing the data. And all the data which is stored in the local network, everybody, if let's say tomorrow I subscribe to this pre-net network, I become part of that network, I need to share some space of mind where the that space is utilized for storing the secure content, in the sense that if person X gives the content, his content is encrypted and it is stored in my computer. And then if some person Y asks that, then the from my computer the content is actually delivered to that user Y. And possibly someone else might also keep a copy of that, and no matter who has that, neither of them, neither I or anybody else who has stored that content, will be able to know what this content is and who is actually making the request. And another key feature of this network was something called as a key-based addressing. There is nothing called URL xyz.com and then you type it on a browser and get the content. Every time I want to access the content, then I need to provide a key. And later people found out that this is actually kind of not scalable. Key is some randomly looking text, alphanumeric character, and then you need to provide that key to get the content. Then they built workarounds to make the life simple, where the users can, just like we are using browsers and there are search engines, similar applications were built on top of this pre-net architecture, and then they were made available for use. So anybody who wants to share the content, there is a concept called as the publishing. So what this does is, let's say I have a movie to upload, which I want to share with all the people on the network. What it does is, this network, it slices that movie into multiple blocks, and each of these blocks are encrypted, and then they are distributed in the network. So maybe let's say a movie is there, a movie one, and that movie is divided into 10 pieces, and each of these 10 pieces are encrypted individually, and then they are distributed in the network. Maybe some 5 to 10 copies of each block are stored in different places in the network. And then when the user asks for a particular content, might be block one might go from my computer, block two might can go from your computer, and block three can come from some other computer, and likewise. So all of them are pulled to the actual recipient, and where it is actually reassembled, it is stitched together, and then a new the original movie was actually rebuilt. Oh, that is the whole philosophy. And as you can see, each of these blocks require the key. It is only through that secret key you can access this content. it become very problematic for the people to remember. Was there a question? Somebody typed something.
Sir, there are few questions in the chat box, sir.
Yeah. So can we go? Let's go.
So the first one is someone is working on Manet,
Okay.
but now it converted in Manet.
Mm-hmm.
I want your kind guidance to develop a new protocol aspect.
Let's not depart from our discussion right now. So these questions will take at the end.
Sure, sir.
Because
Sure, sir.
yeah.
Yes.
So anything related to the content that we are discussing? Okay. I think that so we'll touch upon these questions at the end because that will deviate the discussion. Okay, so a user's computer, how the content is actually located. So as I said, when somebody uploads a movie, it is divided into multiple pieces, encrypted, stored, and then when a user gives a key, then a key there is a automatic key derivation mechanism which was introduced, and that key was you need to get access. So this is an offline mechanism. Initially, they built an offline mechanism to distribute those keys, and then you could get the access to the content. So, but that didn't scale well. So, key distribution become very problematic. Then they introduce some other mechanism. We'll take a look at that. So, the user's computer set out a request for a file key. So, just like the home page of any website is there, similar to that, they built a home page where multiple URLs are encoded, where the indexes of the multiple files are the keys for those multiple files were located, and they said that only the key of the index file, the home page key, you need to get it, maybe from your friend or somebody who is already having that key, who can share with you. If you can get a key for that indexing file, so you can go there, and then just like the URL things, there are encoded, the keys are there. So using those keys, you can get the content whatever you want. And every time some node receives say request for some content through the validated key, so it checks whether the local storage that it has got the content is there. If it has one or more number of the blocks related to that requested content, it will share that. Otherwise, it will pass on the request to the other nodes in the network. And eventually, if everybody start doing this, propagating the request that is received through the network, and it eventually reaches somebody who is having the content, and that guy will pass on the content along the reverse path to the node. So if I ask the question to person X, and the person X doesn't have the content, and he in turn forward it to Y, the data comes in the reverse direction, y to x and x to me. So y will know only x has made the request, who may not be the true consumer, and x will know I made the request, and I may not necessarily be the consumer. So okay, yeah, but in some fashion, so if everybody remembers with whom we asked the question and who actually responded, and based on what they responded, so the data moves in the network. So here is a simple example of how the prenet actually works. On the left hand side, it is the guy A who asked the question, I want the some content. So the blue colored line is the request, the data request that is going. So A is sent to B, and B doesn't have the content right now. It checks its own internal repository. B doesn't have the content. It will just randomly it selects C, and then it goes, okay, do we have this content what the user is asking? And C also checks its local store using that key, and it turns out that C also doesn't have the content. It says, sorry, I don't have the content that you're looking for. And then B continues its exploration. So if C doesn't have, let me try with E. So the request goes to E through that line number 4. And so E checks its own local store, and again it doesn't find the content. So E explores with F, and then F also right now doesn't have the content. So F doesn't know at this moment. The B has already seen this content. It sends one request for the content. B he notices that it is the same request that I sent before. So it says sorry. Then the sorry message comes back to F, and F in turn says sorry to E, and then E tries other paths. So E tries with D. Do you have this data? And then D actually has the data. It provides the data back to E, and then from E to B, the data comes, and finally B handed over to A. In the whole process, D doesn't know that A has made the request, and what it says is only the E is visible to D, and E also doesn't know that E has made the request, but it only said B sent me a request. Let me send that content to B. And B's notion is E sent me this data. I don't know whether E himself has that content, or from somebody else he borrowed and delivered that content. So that is the notion with which the anonymity in the communication is provided. Again, as of now, Prenet is freely available. It is still maintained. It has undergone multiple changes. So if anybody wants to be part of that network, you can download that content within the fraction of few seconds. Just like you become part of the torrent network, so you can be part of the Freenet and then access the content that you want. So now there are the landing pages have been designed, which is called as the pre sites. They have also built search engine within that pre sites. You can give content record just like you do in the Google or any other search engine. You can give a search query, and the prenet in a background network can identify the files and corresponding keys for you. There are also several communities and blogs which have come up on this pre-network, where the keys for popular contents have been populated, and then if you visit those blogs and forums, you will get the key request keys for different content that you are looking for. And nowadays, even there is work undergoing on the key directly exchange. Can the users exchange the key automatically? Yes, seamlessly, just like we do a search engine. So somebody, let's say if I don't have the key and you have that key, so I don't know you have that key, but if I make a request to the network just like publicly, and then can the keys automatically flow to me, and then my computer can automatically pick it that key and make a request, and the content can come. All of this can happen seamlessly without the user noticing any of this. So that's where the thing stands now. So this was the first effort that was made by the network engineers to provide the or bring the anonymity to the communication. With the success of the Freenet and their few users in place, then came the something called as the TOR, which is the primary discussion topic for today's evening. So TOR stands for the Onion Router, and in fact, surprisingly, this was developed by uh, three scientists which are working at the U.S. Naval Research Lab. Although there is a controversy surrounding why the Naval Research Lab should develop something as providing the anonymous communication as star, whatever might be the reason. So there are some controversial reasons why they did so. So basically, they were using this kind of the communication for their own internal data exchange. So they wanted to so if somebody can find out tar is being used in the network, then anybody can make out it is the US naval research data. So if a lot of other people start using the tar, then possibly we can prevent somebody knowing that our conversations are also going over this tar network. That was the primary reason. And just like the pre-net, the tar also provides anonymity, and it provides through a layer of encryption. And through the discussion that follows, we'll try to understand whether this anonymity is absolute, whether what happens. Can we use the TLS in conjunction with the tar? How does it go? So, are there any the bypassing mechanisms with respect to tar? So, all these things we'll try to answer. So, this is how this picture, what you see on this slide, is a depiction of how the tar network actually look like. So, you have a bunch of clients. And by the way, you can use the tar network. The previous one was decentralized peer-to-peer network, but the tar was meant to be used in the client server architecture itself, but still providing the anonymity that is required. So on the left hand side, you have a couple of the clients, and on the right hand side, you have the servers. And the internal network, what you see from this place to this place, is the core tar network. And what it does is, the anytime you want to communicate with or access any server, so all that you need to do is to open the tar browser, which is available freely on the net, and then you type, as if you type the URL in your regular browser. It is actually, in fact, a modified version of the browser that we use. Which is that? Uh, this browser which I logged in. What is this browser? This one, Firefox. So this Firefox source code was taken and then modified to provide the anonymity. So this code is freely available. You install and then you're ready to go. So what this does is, the communication in the tar happen through a layer of encryption. So in fact, you can think of this as the multiple TLS connections being established. And those TLS connections, from client to the first hop, there is one TLS connection. From here to the next hop, there is a second connection. And from here to the next hop, again, there is a third connection. So like this, and then finally from here to here, there is another connection. So over the four encrypted tunnels, each hop actually sees only the left hand side node and the right hand side node, from where he is getting the request and where he is making the forwarding that request to the next hop. Those two entities are known, and nothing else. Again, subsequently, where it is going, nobody, this guy, the first hop node will not be able to know that. So, like this, at any point of time, any node will have visibility of the next hop node to which it is actually forwarding the request, and the previous node from where it actually received the request. Only these two nodes. The idea is the following: the client, the moment when you use the star browser, a node is actually selected as the entry node. So this is also called as the guard node. So the client will have the visibility of only this entry node, nothing else. So and then this entry node will select few random nodes which are part of the star network to relay this content. Sometimes it is one, sometimes it is two, sometimes it is 10, sometimes it is 20, sometimes it is 30, like this. So randomly. So these middle nodes will receive the content and then keep forwarding one after the other. And then at one point of time, so you hit a node called as the exit node, where the tar core is terminating, and then another normal HTTP connection is actually going to the other end, which is where the servers are located. So in this picture, at the minimum, in any tar connection, you need to have three things. One is the entry node, and at least one middle node and one exit node. And the client will not know what exit node is being used for his own or her own connection, and nobody else knows. And the exit node doesn't know to what all clients he or that node is serving as the exit node. And if TLS is used as over and above this, the what the tar provide the connectivity, this channel from the exit node to the application server is also encrypted using the TLS connection. And remember that TLS connection is only between this exit node and this. Is not an end-to-end TLS connection that is established. So this is how the tar is working. Now this is very much a client server communication model, but yet providing the security and also anonymity to the communication. So if you provide these two, then obviously you are also providing the privacy to the end user communications. So that's how tar is actually operating. Now let's understand how this tar this is a connection. The client comes up and then identify in entry node, and you can possibly identify which entry node you want to connect to through some configurations in the browser. And that entry node will randomly select one middle node and the exit node and the server, and the server is sending the data to the exit node, and exit node is sending the data to the middle node, and middle node is sending the data to the entry, and so forth. And when I say the only these things, the one which is sending the data is visible to the next hop, what by that what I mean is the IP address of the server is no longer visible in the middle node. So here I can't find out what is the IP address of the server. So it is only the IP address of the exit node which is available. So this IP address is visible at the middle node. And similarly, the middle node's IP address is visible at the entry node, and entry node IP address is visible at the client. So this is how the tar is actually operating. Now, if I have the option of using the TLS connection over and above the what the tar provides. So I can again have multiple configurations of when I use the TLS without the tar, what will happen. When I use the TLS with the tar, which portion of the data communication is actually visible. So I can have multiple combinations. So here in this case, I can visualize that. So assume you are a home user connected through the Wi-Fi connection, just like I am connected to the network right now. And you do not use the TLS connection, you do not use the tar. What portion, if you are having the some entities in the middle who can read what? So let's say I visit some site .com, and my I am connected to some ISP, let's say the BSNL or Airtel or something like that. So the service provider can actually see the what site I am using. You can see what is available here is also visible at the this is the local service provider that I am connected to, the ISP to which I am connected to. Everything that I'm typing here is visible. If somebody is sitting in the middle, so he can tap to that connection, he can use drop everything. When I don't use the HTTPS and tar. Similarly, if there is some person who is in the middle of the network, this is some ISP because the data communication happen through multiple service providers. At any point of time, if anybody can snip the traffic, he can actually make out who I am and where my request is going, what I am requesting, how much data is going. Everything is visible. So similarly, if somebody is a system administrator who is managing the server, he can obviously read everything that is coming, including the passwords, including the usernames, anything that I am submitting. So this is the case of without HTTPS and without the tar. When I say HTTPS, it is basically the TLS. So if I use HTTPS, but I'm not operating on top of the tar, then what things are visible? So remember, so I am using the HTTPS connection, but now the content the is looking like this. I am typing the site.com and username, some password I'm giving. So if somebody is sitting or eavesdropping in the same network as that of mine, so the any ISP service provider to whom I am connected, they will be able to know what site is being visited by me, in the sense that whether I'm going to some xyz.com or pqr.com, they are able to know. How they are able to get to know? Based on the IP address, because the server has got an IP address, my connection is landing on the server's IP address. So by inspecting that IP address, they will get to know who I am and where I am going, but not to exactly what I am supplying. So you can see this, the password itself is not visible. So username and passwords are now encrypted. So similarly, if somebody is in the middle of the network, not necessarily the ISP that I am connected to, and those people will be still be able to make out where the request is going and from where it came, but not what the username and the password that I have supplied. So, but if you are a system administrator of the target network, then you will be able to see everything, including the username and the password. So, who I am and what password I'm supplying, they will be able to figure it out. So, remember the password that I'm entering with the point where the TLS connection ends, there the decryption happens. So if you want password to be protected, then you need some other mechanism to protect that password. So that won't happen here. So if on the target network, the password will be the moment the TLS connection ends, the passwords will be visible. On the other hand, so if you use only tar but not the HTTPS and the TLS, what things are visible? I am still the same user connected to the same Wi-Fi. So if I type site.xyz.com here, and the moment the I connect to the network, because my traffic is going through the it is encrypted and it is connecting to the entry node, and even somebody sitting at the my own network may not be able to see what site I am visiting. And similarly, the ISP, anybody who is sitting in the ISP will also be not be able to see which site I am visiting and in fact who I am. All of them is hidden. And similarly, if somebody is in the middle, all these relay nodes that I was talking about, the middle nodes, they will also be not be able to know who I am and what I am visiting. And if somebody is at the target ISP, they will be once the last exit node is known. So this is the you can think of this as the entry node and the middle node and the exit node. At the exit node, if you don't use the TLS, then where because the server is outside the tar network, that time the site's visibility will come. And obviously, if you are an adversary sitting in the target network, then the everything would be visible to that, whether you use the tar or don't use the tar, so it will be visible to those users. The last configuration is tar with the HTTPS. So you can see that. So if you use the tar with the HTTPS, none of these guys in the middle, whether it is here or here or here or will be able to make out anything, what site, who is visiting, who is making the request. Only the end user will be able to make out what request came, because it has to serve that request, right? If you ask for some content, let's say a file to be downloaded, it need to identify what file it need to serve to send it back. So that it can do only when it understands the request. So the data and the the exit node's identity will be visible, and by virtue of that, it's actually able to send that data back to the exit node, and then it is relayed to the user. So this is how the visibility changes. So the best configuration to use is if you are using the services which are hosted outside the Tor network, then operate it over the HTTPS and then use the Tor connects browser, and these two combinations will give you the best possible anonymity and security in the on the internet. Now, that's about the how the different the encryption and the security mechanisms that are working on the internet. And Tor, by virtue of doing the layered encryption, multiple hop connections, it is actually very hard to trace who actually did what and how the connection requests actually came. But having said that, there are a lot of legitimate use cases, particularly for law enforcement agencies and activities. So, if something this Tor network, because of the anonymity, it has become a hot cake for people who do illegitimate things. Somebody is selling some drugs or other stuff. They use the Star network to host their content and then sell the this these kind of the stuff. Now, if somebody wants to, if the police or some other investigating agencies actually want to find out what actually happening on the network, so they need to identify the user activities. But how this can be done? So this Tor has been engineered to provide anonymity. Now we want to go towards the de-anonymization. So even somebody is using the Tor, can we predict which website is the user is visiting? So whether you using YouTube.com or whether you using the Flipkart, Amazon, or some other XYZ.com website. So identifying by looking at the Tor traffic, if you are able to tell which website the user is visiting, that is called as the fingerprinting attack. Now, till now, look at the change. Till now, what we spoke is providing the privacy and the anonymity to the end users. Now we are going the other way around to find out the users who is the user and what content he is accessing. This is called the de-anonymization. So as I said, why it is required, there are many legal cases and other scenarios where you require to present yourself. So that is where our works comes in. So this was part of a funded project by the DRDO. Through that, we did this analysis using the machine learning. So basically, we want to collect some traffic and browse some websites and look at the behavior of the content that goes. Content in the sense that I don't have the actual content. So let's say somebody is selling some XYZ stuff. So I don't get to see this is an XYZ stuff, but I can build a profile for the website. So when I visit the Amazon.com website, the content, the number of the packet, the duration of the connection, so the packet sizes, the interval time on these packets look something like this. And based on that model, I'm able to predict this is the Amazon.com website. And similarly, I have a model for predicting the Flipkart. I have a model for YouTube. I have a model for any other website that is of interest to me. and based on that I am able to tell that. This is called as the de-anonymization or prediction, or in technical terms it is called as the website fingerprinting. So now the question comes, if I want to do the fingerprinting, I need to have access to the network traffic. Where exactly I can need to collect this traffic? So one obvious place is between the user. Let's say I am sitting at my home, and this is the node which is available at the ISP, to which ISP I connect. So in between the my computer and the first node of the ISP, in fact, that is the tar node. If I'm able to snip the traffic, then that is one place where I can do collect the traffic and do the analysis. Second is, if I can be positioned in the middle of the network. So remember, there is an entry node and exit node, and then there is at least one middle node. If I can snip the traffic at the middle node, I can still do the analysis. And the third possibility is, if I can get to know what is the exit node that is being used for a particular user. If I can snip the traffic at that place, then also I can do the analysis. And except the first scenario where you are positioned between the user and the first hop node, the remaining two possibilities are very hard to predict, because the tar network has been engineered to select any one random node as the middle node, or multiple number of the nodes as the middle nodes, and any random a possible exit node as the one of the exit node for a particular connection. So in that sense, given for a particular user, even if I have an understanding that you are using a tar, whether your connection itself is flowing through a particular tar node in the middle of the network, I'm not able to predict that. It is very hard to predict, because if, let's say, there are 1 million such nodes, any one of them can be randomly part of this your connection. And moreover, that random node is not necessarily catering to only your connections, but a range of other users which are using the tar browser. So even because your traffic gets mixed with the other 1 million users, so it's very hard to predict. Even if I know that this particular node is actually carrying your traffic, but whether a particular packet is belonging to your own connection or not, that I am is not able to make out, because I have the only visibility of the one hop, previous one hop. So if there are the traffic is routed through 30 hops, then it's virtually impossible to predict who was the original user who made this request. But nevertheless, these are the possible ways where you can snip the traffic and try to build the models. So our analysis was primarily based on the first level entry node. So for a particular user or the corporate network, if you snip the traffic, can we do the some feature engineering and train some machine learning algorithms and try to predict whether this is indeed possible to tell the name of the website. So this is where we set up a test bed with some number of the clients, and we also set up an entry level node which is part of the Tor network, and configure these browsers to select the route the traffic, or select this node itself as the entry node for all their communications. And these virtual machines which are on the left hand side are all acting as the clients, and this is acting as the relay node, and you have some IP address which is assigned to that. Now what we took is, we took some particular websites. These websites are some Alex taken from the Alexa top 100 websites list, and those websites were crawled, in the sense that this particular website is visited some X number of the times, and each time the connection is established, the same website data is collected, and then the feature engineering done, in the sense that when I am using the visiting the Amazon website, no other website is actually parallelly getting visited. So in that sense, I need to have the ground truth. This is the data that is pertaining to the Amazon website. Then only I can do the feature engineering. If the packet one of the Amazon website get mixed with the packet one of the or two of the Flipkart website, then there is no way to figure out this particular packet is actually belonging to this connection, that connection. So even with that demarcation, it is actually pretty hard to do the analysis and then do the prediction. But nevertheless, we tried. This is a very, very good case that you can find. Best possible case to do the prediction. So we actually did some identified some set of the features and then trained some machine learning algorithm, and then our idea was to do a two-level classification or a prediction, where in the first level you do a binary classification. So where we categorize these websites into multiple groups. So you can see this here: e-commerce, Amazon, Flipkart, EBS, Apple, something like that; entertainment related, YouTube, Netflix, IMDb, and so forth; social media, LinkedIn, Reddit, Instagram, something like that; and similarly there are many other groups. So in the first phase, what I'm doing is I'm doing only the category prediction. This is a website which is belonging to the e-commerce. And then once it is identified as a e-commerce, then within the e-commerce, what website it is that I am going to predict. Is it Amazon or Flipkart or eBay? Now that is the two-phase prediction model which this diagram is talking about. So now the question is, why this two? Why not we directly predict the website name? The question we wanted to answer is, let's say, because I don't have the count of exact number of the websites that are out there on the internet, and definitely it is not possible to build a model which can be trained on every possible website on the internet. So there will be, even if I hypothetically train one such machine learning and deep learning model for all the websites that exist today, there is no guarantee that tomorrow there is a new website that is coming up on the net and for which my model is actually not trained. So in that sense, even if I don't know the exact website name, can I actually tell it is the e-commerce website, it is the YouTube, some audio video related website. So that might be helpful in some circumstances. I may not be able to tell exactly the website name, but at least this is actually looking like this is an infotainment related website. That is the main the idea behind this two-page classification mechanism. So what we did is we trained this new model and then checked whether the websites are be able to predict it. Then we could get some good accuracy. This accuracy, don't get misled by this accuracy. So this is a very ideal case where the traffic is completely isolated, in the sense that at one time user is accessing only one website, which apparently is not the case for most of the practical scenarios. We open multiple tabs, open multiple websites, and switch between one tab to another tab. We might even open multiple browsers. We might do many things in parallel. So in that case, it becomes pretty hard. What I'm showing here is the results for a very idealistic scenario where one user, so whose data I'm able to access between the user and the first of node, and then he is at a particular time he is browsing only one website. So for that case, if you have a model which is trained from that particular website, you are able to get this accuracy, and that even tested on some 100 odd website, not more than that. And similarly for other categories also we have some number. So subsequently what we did is the idea was the two-phase classification method idea was to basically predict the something which is unknown. So how good these models are actually in predicting the websites which are not seen before. So what we did is we actually manually excluded certain websites from the training phase, but the corresponding website was included. All of them were included in the testing phase. So this result accuracy, what you see is Excel basically when you exclude none of them, you get 94% accuracy. But if you exclude Shopify, the accuracy falls uh, to 88 percentage. And if we exclude Apple, then it becomes 63 percentage. So like this, when I say I exclude Apple, the remaining all the websites of the e-commerce category is still there. So similarly, if we exclude Flipkart from the training set, the accuracy even falls down to 40 percentage, and similar results for the other cases. So from this set of the experiments, what we could do is if the machine learning model, if it has seen the website before, it does a better job of predicting the name of the website and also predicting the category of the website, but not in the case when the something is not seen before. So in that sense, our true phased idea, this the most of the result that we have got is it's actually a very challenging problem to work on. And many of the places wherever we tested these corner cases, the models were actually failing. So the idea was there were some other research results which were actually advocating it is indeed possible to do the fingerprinting attack, and then our analysis was actually countering that argument, saying that it is not possible to do the predictions, but when it is, where it is falling and why it is falling. So those analysis results we gave. So I have similar set of results for other categories, and so in the interest of the time, I will not go through all those results. Let's take some questions if there are any. Okay. So one of the question is Freenet similar to torrent networks? So it is not similar to torrent network. Freenet is, as I said, is a peer-to-peer network. It is a distributed. Everybody is the server. Everybody is the client. That is the model of the Freenet. It is truly a distributed architecture. And torrent is it is preserving the client server communication model, but yet it is providing the anonymity and security to the conversation that is happening over the internet. Okay. Any other questions? Other than this manet and wanet question, we'll take up this question at the end. Which tool? Which tool is Rajesh Sharma has asked this question. If you download this tool, will it be tagged as virus? You're asking, is that the question? I didn't get you. For last session, that question was for the last session. Oh, okay. Oh, okay. So any other questions? Okay. So let's take up this Manet. Manet was also for the previous this one. Yeah, actually, I asked for support the network, but as per your point, I focused on security. So what was the question? Let me Thank you, man. But now government into Vanet, I want your guidance to develop a new protocol as the ad hoc approach that is supposed to develop. Please. Yeah. This is actually very easiest question to answer in this particular session. So you need to specify the objectives for what you want to address this, why you want to develop this new protocol, what is the reason, what is the issue, underlying issue that you want to address. If that is clear, then you can develop this and possibly try to simulate it. So otherwise it's such an open-end question, so you may not be able to pinpoint answer. Hmm. Any other questions? So if there are no other questions, we'll close the session here. Sorry, I'm actually not well today. And that. So I presume there are no questions. So I'll share the slides if you want to, you can take a look at them. Thank you. Is the Vikas, are you there?
Sir, yes, sir. Hello, sir.
Yeah, yeah. So I'm done with the session, so we can close it for the day.
Sir, so I think there were some questions. So,
I took many of those questions were, I think, for the previous session.
okay, sir. Okay.
So if there are any other questions, I'll be happy to take them.
So so I think if you have covered, so there is no more questions, sir.
HTML DL
Sir,
models are
what
best.
is the conclusion about a study you carried out?
Hold on. Which MLDL models are best for anonymization tools and techniques? So
Just
we tried a range of machine learning algorithms, from SVM to decision trees to all of them. So it is not mainly because of the inferiority of the machine learning algorithms. Many of them do good jobs. In fact, decision tree based algorithms do a good job for classification. But the thing is, what will happen when you present the data which it hasn't seen before? So there, these many of these models actually fail, including the deep learning models will also fail. So we answered peripheral many other questions. So for example, if I train the ML and DL models on the browser version number 1, and these browsers are automatically updated. So if some other user is using an updated version of the browser or a previous version of the browser, so let's say you trained a model on version 2 and somebody else is using version 1 and somebody is using version 3, can these models be used in those cases? Because it is very hard to know which version of the browser the user is using. First of all, it is difficult to identify this is a tar traffic. And even if hypothetically you are able to identify which version of the browser it is actually is using, and whether one version traffic is getting mixed with the other version, so we don't know. That is exactly where these machine learning algorithm models actually fail. So we actually wanted to demystify the claims which are there in the literature. Many of them have shown simply they take this data and train them DL algorithms and say that this is actually 95% accurate. That 95% of accuracy has no meaning if it is doesn't work in practical scenario within the so multiple tabs, multiple browsers, different versions, the website's content being changed. Because websites, YouTube doesn't keep the content static for all the days. New video getting updated, Amazon's new images, new sales come up, the content changes. So if I train the machine learning model using content by browsing the Amazon content today, and tomorrow if Amazon content website content changes, can it still predict it? So these are the scenarios where it actually failing. So we wanted to tell that it is not exactly possible to do the de-anonymization completely. So unfortunately, with those negative results, people don't want to publish the paper. That is a different story. It's okay. So everybody wants to hear only 99% accuracy. So that is where the are you still working on that to extend the research? Yes, we are still working on that one. So we are looking from the problem from the other end. So if I am a service provider, let's say I host a website. So can I predict this request came from a Tor browser or a normal browser like Internet Explorer or the Mozilla Firefox? So from that angle, we're actually looking the problem right now. Okay. So any other question? Yeah.
Uh,
Thank
if,
you.
if there is no more questions, so thank you so much, sir.
Thank
Thank you so
you.
much for the insightful session, and we were privileged to have you on our FTP. And I hope to see you in future FTP also. And I think the number of questions signifies the session itself.
Yeah,
So
sure. Thank you.
thank you so much, sir, for giving us the time.
Thank you.